Hi all, this is section 9 in our CoRec book, and this is of course the prep skills like we always start with. We're going to start with skill 1, which is computing a basic probability, and the simplest way to compute a probability is to divide the number of outcomes in a certain event, so all the outcomes in an event, by the total number of possible outcomes. So you're looking at what are you looking for, and what are all the things that could happen, possible outcomes. So let me make this just a little thicker here. And for example, when flipping a coin, you can either get heads or tails. So there's 2 outcomes, and each one of those, exactly one of those satisfies getting a tail. So the probability of getting a tail is 1/2. So you're looking at how many ways to get a tail on a coin out of all ways to flip a coin. So in this particular case, on a coin, one side of the coin has a heads and one side of the coin has a tail, and so there's 1 way to get a tail and there's 2 ways to flip the coin, heads or tails. So this is what you're looking for. In this case, tails. This is what all the possible. A board game spinner has 8 spaces, numbered 1 to 8. So if you had a, get a little picture here. And if these are numbered 1, 2, 3, 4, 5, 6, 7, 8, and imagine this was, exactly evenly cut up, not, mine's by hand, so it's a little rough, but say each of these was equally likely. If I said for each spin there's 8 possible outcomes, and 3 of those are more than 5. So say we wanted to know the probability of getting more than 5. So that would be 6 or 7 or 8. So out of these total of 8 ways, 3 out of the 8 are what we want. So there's a 3/8 possibility of getting bigger than 5. So the probability, a lot of times what we'll write is the probability of greater than 5 is 3 out of 8. So this is what you're looking for. So up here, if we wanted to write this in the way that they typically write it in the statistics book, we would write probability of tail. Okay, so the probability of tail is the ways to get a tail out of the total ways. Probability of getting bigger than 5 is all the ways to get bigger than 5, 6, 7, or 8 out of the total, which is 8. And now we've covered this a few times, or a couple times, but just a reminder that when you're trying to switch from a percent to a decimal, you're going to take from here and you're going to go back 2 spaces. So 90% and 0.9 are the same thing. So if you've got 0.90 and you're trying to go to percent, that would be 90%. And then if you're trying to go the other direction, if you're in a percentage and you're trying to go back to a decimal, you're going to go to the left 2 spots. It's like dividing by 100. When you go from a decimal to a percent, you multiply by 100. Then if you're going back, you are going to move it left. It's like dividing by 100. 12.5% is 0.125. Because if I take the decimal here and I go back 2 spots, I'm at 0.125. And 4% is 0.04. Remember, if you get a little confused, always do one that you know. Like if you get a little confused on this, you know that 0.25 is the same as 25%. That's one that we use a lot. Or 0.5 is 50%. And so if you get confused, look at one of these ones that you know and think about, well, what would I do to this one? And it's the same process no matter what it is. So to go from a decimal to a percent with 0.25 and 25%, you're going to go right if you're trying to go to the percent, and you're going to go back to the left if you're trying to go back to the decimal. And same thing with 50%, you'd have to move it 2 to the right to get to the percentage if it was 0.5. And if it was at 50%, you'd go 2 to the left to get back to the decimal of 0.5. So always use those as a reference if you need to. Okay, so here's our prep skills questions. Pretty short little prep skills here on this section compared to some of the ones we've done. We're going to start with there's 52 cards in a standard deck, equally divided among hearts, clubs, diamonds, and spades. find the probability of drawing a club when one randomly selected card, and the probability of not drawing a spade. So one of the things that I like to do on this is to look at the sample space because it makes it a little easier to visualize it. So here's a sample space for cards, and it says we want first the probability of drawing a club. So I'm going to do this. Oops, that's not what I meant to do at all. Let me try that again. Okay, so let's do this down here. So we want to know the probability of drawing a club. The clubs are the ones that look kind of like a four-leaf clover with a bottom on it. I think the name actually comes from like the old medieval war weapon that kind of looks like a club that's got like three things on it. I don't know, somebody can look that up if you're interested. But the spades look kind of like little shovels. These are the clubs, and of course these are the diamonds and the hearts. So the probability of a club is out of these, you could either say 1/4 because 1/4 of the suits are clubs, or you could say those clubs, there's 13 of them out of 52. So you can say 1/4 of the suits are clubs, or you can say 13 out of 52, but 13 out of 52 reduces to 1/4. And it's totally appropriate to say 0.25 or 25%. You're going to have to kind of look at what Connect Math wants sometimes, but as far as realistically, it's okay to have any of these answers would be accurate. You'll just have to look at what Connect Math asks for if it asks for a specific form. I think a lot of times it'll say in reduced fraction or decimal. Okay, so then the other one is the probability of not drawing a spade. So if we look back here at the sample set, the probability of not club, or not spade, sorry, we would choose anything that's not a spade. Let's change colors here. So I'm going to circle all the things that are not a spade. The clubs are not spades. The diamonds are not spades. And the hearts are not spades. So all of these cards, except for we don't want to get these because these are the spades. So we're going to count all the cards that are not spades, which would be 13 plus 13 plus 13, which would be 39 out of the 52 cards are not spades. That reduces to 3/4. And again, you could think of it also as 3 out of the 4 suits are not spades, and so that would be 3 out of 4 suits, and just write 3/4 right away. You could also write that as 0.75 or 75%. Another way you could get this 39 is you could say, well, 13 of them are spades. So if I take 52 minus the 13 that are spades, I have 39 left that are not spades. That's called the complement, and you can think of it that way also. All right, so when you roll one 6-sided die, what's the probability of getting a number that's less than 3? Let's change colors here, help us keep track of things. Okay, so if you think of a die, of the faces on a die, a single die, you have 1, 2, 3, 4, and 5, of course. And they want to know what's the probability of let's see, what was it? Less than 3. So less than 3 would be 1 or 2. So those are the two that are less than 3. So 2 out of the 6 faces are less than 3. You could reduce that to 1/3, and as a decimal that would be 0.33. It doesn't tell us how to round, so you could say 0.33, or it actually repeats 0.33333, so you could say 33.3%, and however you want to do that. Sorry, everything kind of ran together here. Kind of separate that out. Okay, so now we're supposed to convert each percentage to decimal form. And if we were going to do that, 87%, remember from percent to decimal, we're always going to shift it to the left by 2. Let me blow this up a little bit. Okay, so if we look at this, 87%, if we shift that to the left 2 spots, that's 0.87. If we look at the 35% and we shift that, or 33.5% rather, and we shift that to the spot left 2 spaces, that gives us 0.335. 9%, if we shift that to the left 2 spaces, that gives us 0.09. Remember, see here we had to go 1 space more than we had a digit for, so we have to put a 0 in there to hold that. Another way to check it is if I went back to the right, 1, 2, I'd have 9%. Same thing here, if I went to the right, 1, 2, I'd have 87, and so on. And then 1.3%, I'm going to go 1, 2. 1 gets me past the 1, but then I have another space here. Actually ends up being 0.013. 0.013. This 0 in front is not mandatory. I just was taught by an instructor long ago that, especially as an instructor, as a teacher, to go ahead and put that 0 because it makes it obvious. You know, like if you do 335 and you aren't real careful about your decimal, you don't make it big or something like that, it can be missed. But if you put that decimal and you put a 0 in front of it, it's pretty hard to miss that that's not 0.335. So I just out of habit put that 0 in front to make it real obvious. So that's it for the prep skills, and we'll pick up with the class and group work here in just a second.
Here we're doing an expected value lab, so you should roll a 6-sided die 100 times, and the idea with the game is that you win in dollars the number that comes up. So I went ahead and rolled a die 100 times and recorded all of the values that came up. Now in number 1, we're supposed to essentially add all of these 100 numbers together, but they have you do it by adding each of the rows together and then totaling that. So I'll go ahead first and add up each of my rows. And then we'll add up all of those row totals, and that gives us a grand total of 336, which means on those rolls we would have won a total of $336. Now in number 2 they ask, what would the average amount per roll be? Well, we won a total of $336 over the course of 100 rolls. So if we divide that by 100 rolls, that's an average of $3.36 per roll. In number 3, they ask us to add up the answers to question 2 from every group in your class. So let's say that you have 6 groups in your class, so the other 5 groups came up with $3.63 per roll, $3.40, $3.60, $3.59, and $3.32. So we'll go ahead and add those up, and that total for all 6 groups comes out to $20.90, and then we'll divide that by 6 groups to get the overall class average, and that comes out to about $3.48. So question 4 says that's the expected value for a roll. It's the average amount that you would expect to win per roll if you played a lot. Is it possible to win that amount on one roll? Well, no, we cannot win $3.48 because every roll wins a whole number. And so it's important to keep in mind that expected value is an expected average, not an expected amount on each roll. Here we're looking again at the dice rolling game, but this time we're going to look at the theoretical expected value. So in question 5, what's the probability of getting a 1 when you roll one 6-sided die? Well, there's 1 1 on it, and there are 6 possibilities. So that probability is 1 out of 6, or 1/6. In number 6, what's the probability of getting any individual number? So what's the probability of getting a 1 versus a 2 versus a 3? Well, for all of those, there's 1 of that number on the die. So every one of those individual numbers has a 1/6 probability of coming up. So with that in mind, in number 7, we're going to think about the expected value. So every one of those dollar amount outcomes has a 1/6 probability. So in this table, we can fill 1/6 in for all of the probabilities. And then to find the expected value, we multiply each of these dollar amounts by their probability of happening. So $1 times 1/6 gives us 1/6. $2 times 1/6 gives us 1/3. $3 times 1/6 gives us 1/2. $4 times 1/6 gives us 2/3. $5 times 1/6 gives us 5/6, and then $6 times 1/6 gives us 1. And then in number 8, it says to find the sum of all of those values in that third column. So we're going to go ahead and add all of those up. And that comes out to $3.50. So that's the theoretical expected value, and that comes out very close to the expected value that we calculated when we actually tried it. We got $3.48. So our empirical expected value when we tried this came out very close to the theoretical expected value. Still thinking about our dice rolling game, in number 9 it says usually you would pay to play a game like this. What do you think would be a fair price? So keep in mind that the expected value theoretically is $3.50. So a person playing expects to win on average $3.50 per roll if they play a lot. So a completely fair price to charge would be $3.50, because in that case you would expect both the player and the person running the game to break even. So then in number 10, would you expect to make money if you were charging students $2 to play? Well, no, you would not, because if they're winning on average $3.50 a roll and you're only charging them $2, that's not going to pay for what you're paying out. But if you charge $5, then you would make money. In 11, they've redone the expected value table to account for charging $2 to play. So from every possible winning, they've subtracted $2 from the amount won. The probabilities for each are still 1/6, and so that changes the final column where they've multiplied the winnings times the probability. And so we will now add up that new third column, and that gives us an expected value this time of $1.50. And that does agree with our prediction in question 10 that if we only charge $2 to play, then the players will still win on average and we will be out that money. Here we're working with a weighted grading scale, and we're shown a sample syllabus with a sample weighted breakdown by category. And we're going to use this to figure out someone's grade. So first of all, in number 1, they ask us to find the percentage of points earned in each category. So for homework, this person earned 220 out of 320. And when you divide that, you get about 68.8%. Group work and class participation, she got 365 out of 410. And that comes out to about 89%. Unit exams. We're given all 4 exam scores, so we actually need to add those up first. And when you add up 77 plus 82 plus 71 plus 85, you get 315. And they were all worth 100 points, so the 4 of them together are worth 400. So 315 out of 400 gives us about 78.8%. And then on the final, they got 162 out of 200, which is 81%. In question 2, it says to use the grading scale to fill in the weights, but we're going to write them as a decimal instead of a percent. So you can flip back to the syllabus and see that the weights are 20%, 20%, 40%, and 20%. So we'll write those as 0.2, 0.2, 0.4, and 0.2. And then 3 says that the points that you actually get for each category are your average times the weight. So we need to do that for each category. 68.8 times 0.2 gives us about 13.8. 89 times 0.2 gives us about 17.8. 78.8 times 0.4 gives us 31.5, and 81 times 0.2 gives us about 16.2. And then 4 says the overall grade is what you get when you add those 4 points together. And so adding those in that last column together, we get 79.3. And so that is this student's grade. In 5, it asks what letter grade this was. Usually with most grading scales, a 79 would be a C, and that is the case here. So she got a C. In question 6, it asks which category had the most negative effect on her grade. So looking back, well, clearly it was the homework. She got high C's and B's in the other 3 categories, but in the homework category, she got a D. So that's the one that's hurting her grade. And looking at the weights, it's not a small weight that's completely insignificant in the grade. It's 20%. In 7, as a check, what should all of the weights add up to? Well, all of the categories should add up to 100%, or in this case, since we wrote them as decimals, they should add up to 1. And they do. What would it mean if they didn't? Well, that would mean that you either have a category missing or you have some sort of mistake in your weights. Here we're going to use a weighted grading scale and figure out what a student needs on the final to get the grade that they want. So in question 8, it says to complete the score column as much as you can. So remember, the points column for each category, or in this case the score, is the average for that category times the weight. So for homework, we'll do 95 times 0.1, and that gives us 9.5. And for quizzes, 88 times 0.15 gives us 13.2. And for unit exams, 89 times 0.5 gives us 44.5. And that's about all we can do. In 9, if you don't show up for the final, what will be your final grade? Well, you need to add together those 3. So we'll add together 9.5 plus 13.2 plus 44.5, and that gives us 67.2%, which is a D. In 10, okay, so if you want an A in the class, what would you need to get on a 200-point final? Well, first of all, let's say in the total grade we want a 90 then. So how much is missing? We've got 67.2, so we would need to do 90 minus 67.2, and that tells us that we need 22.8 for that category. Now remember, the percentage that you get on the final is multiplied by 0.25 to get that number of points. So working backwards, we can take that number of points, divide it by 0.25, and it'll tell us what we need as our average on the final exam. So 22.8 divided by 0.25 gives us 91.2. Let's try it with 91 because they do say that you can assume the professor would round if it came close with standard rounding rules. So let's try a 91. If I put a 91% in for the final exam and I multiply by 0.25, does it round to 22.8? And it does. It comes out to 22.75. So that would do it. I need a 91 on my final exam. It's a 200-point final. So a 200-point final times 0.91, because that's the percentage we need to get on that test, comes out to 182 points. So this person needs 182 points on the final to get an A. Now that you've been through a weighted grade example and have hopefully seen how similar that is to expected value, we're going to do another expected value example. So we have a carnival game here where you spend $2 to play, and then you earn different dollar amounts depending on what color the pointer lands on. So looking at question 11, they've started the table for you. Red wins you $3, but since you paid $2 to play, you only really gain $1. Yellow wins you $2, but that means since you paid $2, you don't really get anything. Purple, you got nothing, so you were actually out the $2 you paid to play. And then blue wins you $5, and so since you paid $2 to play, blue would actually only gain you $3, and that one we do need to fill in. In 12, we need a probability for each color. So we're going to need to look back at the spinner. There are 8 different equally sized portions on this spinner. And so for red, 2 out of the 8 are red. So that'll be a 2 out of 8 or 0.25 probability for red. And then for yellow, also 2 sections that are yellow. So that will also be 0.25. For purple, we have 3. So 3 out of 8 gives us 0.375. And then blue, there's only one section that's blue. So 1 out of 8 gives us 0.125. And then 13 asks us to fill in the final column where we multiply the dollar amount by the probability. So for red, $1 times 0.25 gives us a quarter, $0.25. Yellow, 0 times anything is just going to come out to 0, so nothing there for yellow. Purple, -2 times 0.375 gives us -75 cents. And then blue, $3 times 0.125 gives us 0.38 cents. And then number 14 asks us to find the expected value. Well, to do that, we need to add all of those products we just found in the final column. So when we add all of those together, we get -12 cents for our expected value. And what does this tell you? This means that if you played this game over and over and over, in the long run, you'd expect to lose about 12 cents for each spin. In 15, a game of chance is called a fair game if the expected value is 0. Why do you think that is? Well, an expected value of 0 means that you expect to break even in the long run. And that means that the person running the game will too. So both sides are breaking even. In 16, from the player's perspective, a game favors the player if their expected value is positive and favors the house if their expected value is negative. Is the spinner game fair? Well, looking back at the expected value, we found that it was -12 cents. So that is not a fair game, and it favors the house because it means that the player expects to lose money in the long run. In 17, if you played this game 100 times, how much would you expect to win or lose? Well, since the expected value is negative, you expect to lose money. We expect to lose an average of 12 cents per game. So if we expect to play 100 times, that would be 100 times -12 cents, and that comes out to -$12. So you would expect to lose about $12. This is talking about how to calculate a GPA, which is actually an example of weighted grading. So in question 1, it says that in most GPA systems, an A is worth 4 points, B is 3, C is 2, D is 1, and you don't get any credit for an F. So filling in the grade value column in this table, the A in English is worth 4 points. The C in math is worth 2, the B in history is worth 3, and the D in science is worth 1. And then question 2 says the credit hours are the weights. So to get the number of points for each class, we're going to multiply the grade value times the credit hours. So for English, 4 times 3 gives us 12 points for that class. In math, 2 times 4 gives us 8. In history, 3 times 3 gives us 9. And in science, 1 times 5 gives us 5. Now in 3, it asks us to total the credit hours and the grade points. So the total credit hours comes out to 15 hours, and if you add up all of the grade points, it comes out to 34. And to find a GPA, you take the total grade points and divide it by the total credit hours. So we'll do 34 divided by 15, and we usually round to 2 decimal places for these, and it comes out to 2.27. In 4, it asks, what would the GPA been if all the courses were weighted the same? Well, looking back, that would mean that you wouldn't need to multiply each one by the credit hours because they would all be worth the same. You could just take all of the grade values and average them. So let's do that. We've got a 4, a 2, a 3, and a 1. So 4 plus 2 plus 3 plus 1, and then we'll divide the whole thing by 4 because there are 4 of them. We're just averaging it, and that would be 10 divided by 4, which would give her a 2.5. So the weighting of the classes with the credit hours does make a difference. Here we're looking at a carnival game where you win different dollar amounts depending on what number you roll on a 6-sided die. In question 5, they want you to think about whether you think this game sounds fair and whether you'd be willing to play it. So that's a personal question. Think about your own response. For me, just in general, on principle, math teachers tend not to gamble because we know a lot about probability and stuff. In question 6, we're going to find the expected value for this game, and they've given us a table to organize our work. First, we need to think about, for each number that we roll, what amount do we win or lose. So if we roll a 1, we win $1. If we roll a 2, a 3, or a 4, we lose $2. So that'll be negative $2. And then if we roll a 5 or a 6, we win $3. So that's positive $3. And then we need the probability of winning each amount. So to win $1, there's only one number that will allow you to do that. So that's 1 out of 6 or 1/6. And then to lose $2, there are 3 numbers that do that. So 3 out of 6, which reduces to 1/2. And to win $3, there are 2 numbers that do that. So 2 out of 6 reduces to 1/3. Now we need to multiply each win or loss by its probability to fill in the final column. $1 times 1/6 gives us 1/6, but since we're working with money, let's round that to 2 decimal places. So that would be 17 cents. Negative $2 times 1/2 gives us negative $1. And $3 times 1/3 gives us positive $1. So to find the expected value, we need to add all of those up, and that comes out to 17 cents. In 7, would you prefer to be the player or the person running the game? Well, because that expected value came out positive, you would prefer to be the player because that means that in the long run, you expect to win money. So you'd rather be that person than the one running the game who's paying that money out. And in 8, what should the player expect to happen if he plays the game 500 times? Well, in the long run, we expect to average 17 cents per game. So if we play 500 times, that'd be 500 times 17 cents, which is $85. So you would expect to win about $85. Although remember, with probability, this cannot be guaranteed. Here we have a weighted grading scheme for a Calc 2 class, and we're asked to find a person's grade given all of their scores in each category. So I've set up a table like the one we used earlier in the lesson. First, I'm going to fill in the different category names. We've got tests, quizzes, final, homework, and projects. And then we need to find the student's average for each of those categories. So in test scores, we have 4 different scores, and those 4 different scores are all out of 100. The scores the student got add up to 323 out of 400 points possible on those 4 tests. So rounding that to 1 decimal place, that's about 80.8%. And so that's what I'll fill in for the test average. For quizzes, we just need to do 140 divided by 150, and that comes out to about 93.3. For the final, 175 divided by 200 comes out to about 87.5%. For homework, 88 divided by 94 gives us about 93.6%. And for projects, we have 2 scores. They add up to 88 points out of 100 possible. So that's an 88%. And that's what I'll put for the project average. Now we need to write in the weights for each category in decimal form. So tests are worth 40%, that's 0.4. Quizzes are worth 20%, that's 0.2. The final's also worth 20%, so it's 0.2. Homework is worth 10%, so that's 0.1, and projects are also worth 10%, so those are 0.1 as well. Now to find the points that you get towards your grade for each of these categories, we need to multiply the average times the weight. So 80.8 times 0.4 gives us about 32.3. 93.3 times 0.2 gives us about 18.7. 87.5 times 0.2 gives us about 17.5. 93.6 times 0.1 gives us about 9.4. And 88 times 0.1 gives us 8.8. So to get this person's grade as a percentage, we can add all of those points together, and that total is 86.7. So this person's grade is an 86.7%.